Hello and welcome to Aero Engine Gas Turbine Cycles, lecture 31. So, in last lecture we were given with this numerical and I asked you to solve this numerical and we will check with the solution today. So, we have two spool turbofan engine which is at the preliminary design stage. The conditions are flight altitude, it is given 12,000 meter, flying Mach number is 0.82, free stream temperature and pressure are 216.65 Kelvin and 19.33 kilopascal. Here in this case fan pressure ratio is given 1.6, compressor ratio is 20, bypass ratio given is 5.6, turbine entry temperature is 1.73 Kelvin. Total pressure loss in combustion chamber is 3%. Calorific value of the fuel is 42,800 kilojoule per kg. Total engine mass flow rate is 120 kg per second and it's given say bleed air, it is been taken at temperature of 500 Kelvin and pressure of 261.42 kilopascal, and this is say 20% of core mass flow rate. We are also given with the isentropic efficiencies of different components, say diffuser efficiency is 98%, fan efficiency is 88%, compressor efficiency is 84%, combustion chamber efficiency 96%, turbine efficiency 94%, nozzle efficiency it is 95%, and it says specific heat for air is 1.4 and specific heat for gas it is 1.33, and we need to calculate what will be the velocities, thrust specific fuel consumption, thermal efficiency, propulsive efficiency and overall efficiency. So, as we have discussed, we need to read the data carefully. We can realize here it is given say fan pressure ratio and compressor pressure ratio. That means, we are not having any bifurcation in terms of HP compressor and LP compressor. That means, my LP will be running my fan and my HP compressor will be running all compressor stages. So, that need to be clear here only. One more thing, it says total engine mass flow rate it is given, that is the mass flow rate with which air is entering inside the engine. So, with this data let us try to get the solution for. So, we have also discussed the solution, how do we proceed with. For different components, different parameters which are given to us, from those parameters we will be calculating the exit condition which may be the inlet condition for the next coming component, and that is how we will be reaching up to say last component say nozzle. So, we are having two nozzles here, one it is turbine nozzle and second that is what is our fan nozzle, and based on that we will be calculating what will be our exit velocity. Now, once the exit velocity that is known to us, we can calculate what will be the thrust, we can calculate what will be the thrust specific fuel consumption, we can calculate what will be the efficiency say like thermal efficiency, propulsive efficiency, overall efficiency, and that is how we will be solving this numerical. So, let us start with very first component. Before going into the detail, as we have discussed, we need to first make the line diagram. So, here as we were discussing, since my fan pressure ratio it is given, compressor pressure ratio it is given, that is the reason we can say my LP turbine that will be running only the fan and HP turbine that will be running all compressor stages, and somewhere at some location we are having the air bleed, and this is representing our TS diagram or HS diagram, that is also equally important. So, that once we have the information about all the stations, it will be easy for us to calculate the parameter and we will not commit any mistake. Since we have discussed, we are having 2 points here, 2 nozzles. So, one expansion from 8 to 9 it is for the turbine nozzle, and from 3 to 10 that is what is representing my fan nozzle. Okay. So, now let us move with the case. Here in this case my flying condition, it is given say engine flow, that is what is entering at Mach 0.82. We can say this is the flight Mach number or aircraft Mach number. Now, what we know, very first component we have is our intake. For that we will be calculating what will be our free stream velocity. So, this free stream velocity based on Mach number, it is coming 241.93 meter per second. Okay. Now, next we have is our diffuser efficiency. We have correlated our diffuser efficiency with Mach number in terms of our pressure ratio. So, we can say my outlet pressure from the diffuser, that is what will be given by this formulation. Since the diffuser efficiency is given 98% and Mach number it is given 0.82. So, putting these numbers, the exit pressure, inlet exit pressure or intake exit pressure is coming 29.81 kilopascal. Okay. Now, in line to that we will try to calculate what will be our exit total temperature. So, exit total temperature we are correlating based on this isentropic relation. For this, free stream Mach number is known to us. So, we can calculate the exit total pressure from the intake, and that is coming 245.79 Kelvin. Now, this will be the entry condition for my fan. Okay. So, next component we will be selecting, that is fan. So, for fan we are given with the pressure ratio of 1.6. So, based on that pressure ratio we can calculate outlet pressure from the fan. This outlet pressure from the fan is coming 47.69 kilopascal. Now, we also know our temperature ratio, that is what is a function of the pressure ratio and fan efficiency. Here nothing it is mentioned in terms of number of fans. So, we can consider there is only one fan, and for that we are considering only fan efficiency. So, if we will be putting say our compression ratio, it is 1.6, fan efficiency is 88%, we will be calculating our exit temperature, fan exit temperature, it is 285.93 Kelvin. Now, this will be the condition for the entry of our compressor. At the same time we are having bypass duct. So, this could be the entry condition for the bypass nozzle. Okay. Now, let us move towards the next component, that is our compressor. For this compressor it says compression ratio is 20. You can imagine if this is 20, number of stages required for the compressor will be higher. Okay. And let us see, if this is 20, we can say exit pressure from the compressor will be 953.92 kilopascal. And let us calculate the temperature. This temperature we are calculating based on our temperature ratio. This temperature ratio is a function of pressure ratio and compressor efficiency, that is our isentropic efficiency. This isentropic efficiency is given 84% and pressure ratio is given 20. So, we will get the compressor exit temperature to be 746.67 Kelvin. Okay. Now, here in this case, this pressure ratio at this moment it is given data. Maybe when you are doing your actual engine design, you will be playing with the number. That is what we are discussing at the end with the effect of cycle parameters on performance, and that is how we will be using this information for making say innovative or the new kind of engines. We need to be very careful here in terms of selecting this parameter. Suppose say this compression ratio we are taking say 20:1, maybe that can be taken 30:1, maybe you can take 40:1, no one will stop, but what will stop us? That stopping parameter, that is what will be our turbine entry temperature. So, you need to be very careful in terms of selecting this pressure ratio for the compressor. As and when this discussion will come, we will discuss this point. Okay. Now, what we have our next is our combustion chamber, and for this combustion chamber it says my total pressure drop is 3%. So, that is what will be giving the exit pressure from the combustion chamber as 925.3 kilopascal. Okay. Now, we know this is our combustion chamber. If we will be putting our mass balance, then mass, that is what is entering inside, that is what is correlated in terms of outlet also. So, let us put that in terms of our energy balance, it will give the more clarity. So, what we say here, we are having the bleeding, that is what we have done at some station at some temperature and pressure from the compressor, and that is the reason why mass flow rate, that is what is entering inside the combustion chamber, that will be less by this fraction 1 minus B fraction. Okay. Same way here, what we say, it is a fuel that we are burning inside the combustion chamber, that is having the efficiency MF into calorific value of the fuel. Same way at the exit, we can say the amount of flue gas that is coming out, it is m dot core into 1 plus F minus B, and that is what will be raising our temperature to T05, or we can say our enthalpy is H05. Okay. So, let us put the energy balance here. When we are writing this energy balance, it says my fuel air ratio, it is given by this equation. Here it is multiple by 1 minus B. Be careful about that part. Okay. Now, H05 we are writing in terms of Cp T05, but here this is at high temperature, that is the reason why we are saying Cp of hot gas. Same way this H04, it is exit of our compressor, that is why we are saying Cp of cold air into T04 divided by my combustion chamber efficiency and calorific value minus T0 H T Cp T05. Okay. So, if we are putting all these numbers, the fuel air ratio, it is coming 0.0215. Okay. So, from that we are able to calculate what will be the amount of fuel, that is what we need to add in order to reach that temperature. Okay. Now, let us move towards the next component. What next component we have is our HP turbine. Since we are having air, it is being bleed at some pressure and temperature. So, we can write down our work balance. So, HP turbine, it is been used to rotate our compressor. So, for all compressor stages, the equation we can write down like this. So, be careful here, this is given by mCp T03B minus T03. The reason is, after this point we are extracting the bleed air, that is the reason why it is difference of this. Here if you look at remaining air, that will be going from T04 minus T03B. Similarly, on other side for the turbine, we can write down m dot core into 1 plus F minus B Cp T05 minus T06. Now, since T03B and T03 they are known to us, T05 also is known to us, we can calculate what will be the turbine exit temperature. So, this exit temperature we can write down like this. Okay. Here again we need to be very careful in terms of units. So, Cp value what all we will be taking, we will be taking that in terms of joule per kg Kelvin. Okay. So, if we will put these numbers, the temperature at the exit of HP turbine, it is coming 1134.2 Kelvin. I am sure you have understood what we mean in terms of bleeding of air, because this we have discussed in last lecture. Okay. Now, let us move towards say calculation of exit pressure from the HP turbine. We know what is our turbine efficiency. This turbine efficiency can be correlated in terms of our expansion ratio, or we can say pressure ratio, it is P06 by P05. This efficiency, it is given 94%. Temperature values are known to us. if we will be putting these numbers, we will be getting the exit pressure to be in the range of 2 to 3.9 kilopascal. Okay. Now, let us move towards the next component. What next component we have is our LP turbine, and for this LP turbine, as we have discussed, that is used to rotate the fan. So, my fan work, that is what will be equal to my LP turbine work. This fan work we can write down in terms of m dot core into 1 plus beta CPC T03 minus T02. Same way here on this side also you will be having m dot core. So, that is what will get cancel out with. And if you will be writing this equation, it says my T07, it is my LP turbine exit temperature. We can calculate, it is coming as 851.64 Kelvin. Okay. So, now in order to calculate what will be our LP turbine exit pressure, we have our formula for the efficiency. This efficiency formula we can represent in terms of pressure ratio, and this pressure ratio will be giving us the value of exit pressure, and if we calculate this value, this is coming as 64.73 kilopascal. Okay, so, this will be our turbine exit pressure. Now, here in this case we are not having any tailpipe information, that is the reason why we are not considering that as a parameter. What we will be considering? The gas which will be coming out from the LP turbine, that is what will be exiting from the nozzle. We can say that as a core nozzle or the turbine nozzle. So, for nozzle calculation or say nozzle pressure calculation, we will be calculating first with the critical pressure ratio. So, here this is represented in terms of P08 by Pc, that is the function of my nozzle efficiency. Be careful, my exhaust gas will be hot gas, that is the reason why gamma value it is for the hot gas. So, let us put this number, and if we are putting this number, the critical pressure it is coming as 33.77 kilopascal. What we will be doing now? We will be comparing this with our atmospheric pressure. So, it says this critical pressure is greater than that of our atmospheric pressure. Our atmospheric pressure is 19.33 kilopascal. Okay. So, we can say our nozzle it is choke nozzle, and for that we can say exit pressure equal to critical pressure, and that is 33.77 kilopascal. Now, let us calculate the temperature. So, we have our temperature ratio, it is given by, for the choke nozzle it is given by gamma plus 1 by 2, and if we are putting this number, the static temperature at the exit of the nozzle, that is 731.02 Kelvin. Once we have this temperature, we can calculate turbine nozzle exhaust velocity, it is gamma RT9. This gamma value, R value and temperature value, they are known to us, and that is giving the exhaust velocity from the turbine as 528.24 meters per second. Okay. Now, the next component we will be selecting is our fan nozzle, and for fan nozzle we are having our critical pressure ratio as P03 by Pc. For fan also we are knowing say efficiency of this nozzle, maybe at some instant for nozzle efficiency for the fan and nozzle efficiency for the turbine or the core engine, this number may be given different. So, you need to be careful in sense of writing this information. Same way here in this case, this value we are putting as gamma. Okay. And if we take this as gamma, that is 1.4, and our efficiency is 95%. So, based on that we will be doing our critical pressure calculation. This critical pressure is coming as 24.28 kilopascal. Now, we will be comparing this with our atmospheric pressure. The atmospheric pressure is 19.33 kilopascal, that means this nozzle also is a choke nozzle, and for that our exit pressure will be critical pressure, and that is 24.28 kilopascal. Okay. Once we have information about this pressure, let us try to calculate what will be the exit static temperature. Since it is a choke nozzle, so we will be writing the temperature ratio by gamma plus 1 by 2, and if we will be putting these numbers, the exit temperature is coming as 238.27 Kelvin. Now, for the choke nozzle exit velocity, it is given as gamma r T10, and this value it is known to us. So, we will be calculating our fan nozzle exit velocity as 309.42 meters per second. Okay. So, now here this will give the idea about the calculation of all cycle parameters. When I say cycle parameters, our major concern is with pressure and temperature, and if you look at carefully, we are more interested in total properties. Only for nozzle we are selecting or calculating the static property, because we want to calculate ultimately what is our velocity, and that velocity it is a function of static temperature. Okay. Now, in order to do the calculation for the thrust, we know we need to have the area of both the nozzles. So, let us try to calculate the area for both the nozzles. So, here in this case, this is the formula for our thrust. This thrust we are writing in terms of cold thrust and hot thrust. So, A10 is nothing but it is a area of fan nozzle, A9 it is the area of our turbine nozzle. Okay. So, here in this case, if you look at the numbers carefully, it says we are given with the total mass flow rate. At the same time, we have information about the bypass ratio. So, this bypass ratio we are writing in terms of say bypass airflow divided by primary airflow, and from that we will be doing the calculation. It says m dot fan divided by m dot core. So, from that we will be calculating our value for m dot core, and this m dot core is coming to be 18.18 kg per second. Now, just realize this thing, this is required for the calculation of area for the turbine nozzle. Okay. So, we can write down what is my M9. This M9 we are writing as say it is density into area into velocity. So, here this M9 we are writing in terms of m dot core into 1 plus f minus beta divided by V9 into density 9. Here also this density value it is not known to us. So, this density value we can calculate here by P9 by RT9, and this we are writing in terms of say pressure and temperature. Be careful, this pressure we are writing in terms of pascals, and R value that is what we are taking in terms of joule per kg Kelvin. So, if we are putting these numbers, the density is coming 0.161 kg per meter cube. Now, once this density is known to us, we can calculate what will be the area, exit area. It says after putting these numbers, the exit area is coming 0.175 meters square. So, this is the area from our core nozzle, okay, or this is the area of our turbine nozzle. Similarly, we can do our calculation for our say main nozzle, fan nozzle. Here in this case, be careful, we are given with this mass flow rate. This mass flow rate we are calculating based on this. So, my fan mass flow rate we know we are representing in a different way. So, this fan mass flow rate we are writing as say density into area into velocity. So, be careful what we mean by total mass flow rate, what we mean by core mass flow rate, and what we mean by fan mass flow rate. Okay. We should not get confused here. Okay. This is the mass flow rate, that is what is passing through my bypass duct, and that is what is important for the calculation of my exit area. Okay. So, if that is the case, we can calculate what will be our density. It says it is P upon R T, and this value if we are putting, my density is coming to be 0.355 kg per meter cube. Once this density is known to us, we can calculate the exit area, and this exit area is coming to be 0.927 meter square. Okay. So, now in order to calculate the thrust, the unknown parameters like both the areas, they are known to us. Okay. So, let us put these numbers in the thrust equation. So, this is my thrust equation. Okay. This thrust equation we are writing here, say V9, V10 we have calculated, V infinity also we know based on our Mach number. If we will put all these numbers, it says the net thrust is coming 17.48 kilonewton. Okay. Just realize this number is on lower side because we are considering the flying condition, okay, where in this formula we are having this V infinity term, that is what is coming both for hot and cold thrust calculation. So, do not get confused with this part. Okay. Now, the next parameter what we have is my thrust specific fuel consumption. This thrust specific fuel consumption we can correlate by fuel air ratio and n dot core, and this is coming to be 0.0223 gram per Newton second. Okay. Now, what next parameter we are expecting is our efficiency calculation. So, let us try to write down very first equation for propulsive efficiency. We know it is V into T, that is what is my net thrust. Here we are writing in terms of hot thrust and cold thrust, and this is representing my kinetic energy part. Since we are having our V infinity here, that is the reason we will be having our propulsive efficiency, and this propulsive efficiency is coming to be 83.37%. Okay. In line to that, we can calculate our thermal efficiency. We know this thermal efficiency we are correlating in terms of denominator divided by our MF into CV value. If we are putting this number, that is giving the thermal efficiency to be 30.34%. Okay. Now, once this thermal efficiency is known to us, we can calculate our overall efficiency, and this overall efficiency we are writing in terms of thermal and propulsive efficiency. That is what we are getting in terms of 25.29%. Okay. Now, this is what is a solution for what numerical we are discussing, that is for the flying condition. Okay. So, let us try to put this in terms of say our cruise condition calculation. Here we can say we have our flying condition, temperature and pressure, they are known to us. We have done calculation for both the areas. Same way here we are having our net thrust calculation. We have done calculation for thrust specific fuel consumption. We have done calculation for propulsive, thermal and overall efficiency. Okay. So, this condition what all we have solved now, that is for the flying condition. So, let us try to understand, suppose if I consider I am doing my calculation at the ground condition. So, for that purpose, say here I am giving you a numerical. So, this you need to solve the way in which we have solved the last numerical. So, it says we are having 2-spool turbofan engine at the preliminary stage. The information we are putting same, because we want to compare what is the performance parameter change with the change of cycle parameters both for your flight condition as well as for the ground condition or sea level condition. So, this numerical we will be solving for say our ground condition, where temperature is 288.15 Kelvin, pressure is 101.325 kilopascal. Our fan pressure ratio is 1.6, compressor pressure ratio is 20, bypass ratio is 5.6, turbine entry temperature is 1573 Kelvin, total pressure loss in combustion chamber is 3%, fuel heating value is 42,800 kilojoule per kg, total engine mass flow rate is 485 kg per second, bleed air that is taken as 585 Kelvin, and our pressure is 888.58 kilopascal, and that is at 20% of my core mass flow rate. Okay. And the efficiency values, they are same as what all we have discussed. Okay. And we need to calculate what will be our say velocities, what will be thrust specific fuel consumption, thermal efficiency, propulsive efficiency, and overall efficiency. Okay. Now, again let us give this solution. Say we have our components similar to what all we have solved for our earlier numerical. Here in this case it is given my m infinity is 0. So, we will be calculating our exit conditions from the inlet. Same way for the fan, pressure ratio and efficiency, they are known to us. We will be calculating what will be the exit pressure and exit temperature. Next component we have is our compressor. For the compressor, the information given is pressure ratio and efficiency. Based on that, we will be calculating what will be the exit pressure and exit temperature. The component what we have here, it is our combustion chamber. For that, we will be calculating what will be our fuel air ratio. We have our HP turbine, we have say our LP turbine. For both the cases, we are having this bleed, that is what is given to us. So, we need to take care in terms of calculating the pressure and temperature, both for HP turbine as well as for LP turbine. The next component we have is our turbine nozzle, we have our fan nozzle, and we will be calculating the exit velocity, exit static temperature, exit static pressure, and based on that we will try to calculate the performance parameters. So, here we are stopping with this lecture, and let us get the solution for this numerical. In next lecture, we will be discussing about the performance, what will be the effect of different parameters on the performance of our engine, and that is what will be giving some other idea. So, thank you very much. We are stopping here.